So today we are going to cover the last part of processor logic design, and today we will mainly focus on control logic design. In our last class, we have seen how to write the control word for the microoperation. Okay, we have written different control word for different microoperation, and also we have seen the flowchart and state diagram of two's complement, addition, and subtraction. Today, we are going to write the microprogram control unit that will perform the entire operation to complement, addition, and subtraction. So, first step, we need to write down the control word so that we can write the microprogram. Okay, so let's find out what will be the control word for the operation to complement, addition, and subtraction. So, this was our data processor and part, like this data processor part contains the ALU shifter, okay, different component, input data. Then the data get processed by the control unit with the direction of the control unit. Control unit generate the control signal, and according to the control signal, data processor part perform the operation. So we have seen the data processor part in our last class and the class before, okay, the ALU design, shifter design, okay. And today we will focus on the control logic design. Okay, and this control logic design we are going to do for two's complement, addition, and subtraction. We have seen the flowchart and state diagram in the last class. So this is the different methods of control unit design, and we are focusing on the microprogram control unit. This is the three block of the microprogram control unit: next address generator, control address register, and the control memory. So today we are going to write the microprogram for the two's complement, addition, and subtraction, and we'll store the microprogram in the control memory. And also we design the hardware for the next address generator. So these are the steps. The problem is started, an initial equipment configuration is assumed, an algorithm is formulated, the data process part is specified. We have done up to step 4. Today we will do the control logic is designed. Step 5 we will focus on today. So we have seen the algorithm behind the two's complement, addition, and subtraction in the last class. This is the equipment configuration, and this is the analysis. Okay, and based on the algorithm, this is our flowchart, and this is the control state diagram. Now is the time we are going to do the design. This is the data processor part. Okay, this is the data processor register. This is the register A, hold the word A. This is the register B, hold the word B. This is the arithmetic logic unit that we have designed. Mode select pin, H raised is the function select. This is the carry in. The carry out. This is the overflow bit. E. What is the overflow bit? Sign bit of B, sign bit of A. Now, to control or work with this overflow bit, sign bit of A and sign bit B, we need few other control signal. For example, the W control signal. Look at over here. This W control signal. This will be used to set or reset the overflow bit. Z control signal will be used to set or reset this sign bit. Y control signal. This will be used to set or reset the sign bit of B. Okay, and this is the another control signal we need, load. This signal will be used to load the result in the array register, or load the word A in the array register. Also, it will load the overflow bit. It will load the overflow bit. So this S2, S1, S0, S carry in, these are the control signal we have already used before. You already know how they are used. So few other control signals L, W, Z, and Y are required to perform this data processing part. Okay. So 4 new control signal L, W, Z, and Y. Okay. Now, as you have seen in the last theory class, the S bit, okay, exclusive OR of sign of A and sign of B is the S bit. From the flowchart, we know that by using the exclusive OR operation, we get the S bit. Okay. So these are our input of our control logic. QA for addition operation, QS for subtraction operation, sign bit of S, A, sign bit of A, and sign bit of B, and the S is the exclusive OR AS, exclusive OR BS. Okay, this is the S bit. And one more control signal we need at the input part is the E. Okay, what is E? Is the overflow bit. Okay, so these are the input of the control logic, and this is the output. X is the initial state S2, S0, S1, carry in L, Y, Z, and W. This will be the output control signal that will control the operation of our system. So this is the logic we are going to design. QA, QS, S, and E is the input, and these are the output. And what we need to do? We need to design the hardware for it. If you design the hardware for it, that process is called hardware control unit. And instead of hardware, if you use a microprogram, that will be called microprogram control unit. Our target will write the microprogram. Okay, so let's do it. Look at over here. Based on this state diagram and this flowchart, what are the operations at different state? At state T0, what are the operations happening? The state T0, x equal to 1. Look at over here. At the state T0, x equal to 1. Initial state x equal to 1. Okay. At state T1, what you do? You take the complement of sign B. At T2, T1, you take the complement of sign B. Okay. At T2, what you do? You do nothing. Okay. At T3, what you do? At T3, you perform addition. Look at over here, A plus B. At T3, you perform addition, A plus B, and carry out, go to the E, overflow bit. Okay, A plus B at T3, A plus B, and carry out, go to the overflow bit at T3. This is T3. T3. Okay. At T4, what you do? You perform subtraction, A plus B bar minus 1. You see at T4. A plus B bar minus plus 1. That means A minus B. You perform subtraction and carry out, go to the A list. That's at T4. Okay. At T5, what you do? At T5, you send 0 to the A. Okay. You clear the overflow bit. That's T5. That's T5. Okay. No. These all the things, this flowchart, this state diagram you need to draw, and this is also you need to draw by yourself. Nothing will be given. Okay. At T6, what you do? From your flowchart, you will do it. Okay. At T6, you can find this is a flowchart. You take complement of A. Okay. You take complement of A. This is the complement of A. At complement of A. This is the T6. At T7, what you do? T7. You see? A bar plus 1. No, A plus 1, right? A plus 1. This is A plus 1. A plus 1 goes to A. And you complement the sign of A. Complement the sign of A. That's T7. Okay, on your question paper, usually they will ask for, okay, write the control, microprogram on. Write the microprogram. Write the microprogram. They'll ask you to write the microprogram. So to write the microprogram, these are the steps. First, you need to find out what operations are happening at different T state. Then, to perform this operation at the different T state, what will the control want? Let's find out. Okay, so let's translate this operation to the control one. What will the control want for this operation x equal to 1 at T0? So there are several steps, T0 to T7. Look at over here. Several steps, T0 to T7. And this is the output of the control unit. This is the control logic, control unit, and this is the output. So these are the output: X, S2, S1, S0, carry in L, Y, Z, and W. So to perform this operation T0, what will the control output? What will the define bit pattern over here? Okay, let's find out. At T0, x equal to 1. At T0, x equal to 1. And other control output will be 0. So all other control output are usually 0. T0. At T1, look at over here. At T1, what you do? At T1, you change or complement the sign of B. Okay? At T1, it complement the sign of B. So at T1, how you complement the sign of B? Look at over here. The signal Y. If you can generate the signal Y, that will complement BS. So the signal Y, look at over here. The signal Y is 1 to perform that operation. All of the control output signal will be 0. Yes, this can be given or may not be given. If it is given, that's fine. Or if it's not given, you need to draw it by yourself. Okay. So that's T1. Let's look at T2. At T2, do nothing. So look at what at T2, all are 0. At T3, what you do? At T3, look at what here. A plus B, addition operation goes to A, and carry out goes to overflow bit. So what is A plus B goes to A? Addition operation. Look at over here. This is table. This is the table for the arithmetic logic unit. Look at over here. Function A plus B. Okay, and carry out goes to E. So to perform this addition operation, what you need? You need this bit sequence. S2 should be 0, S1 is 0, S0 is 1, carry it to 0. So S2, look at over here. This is the bit sequence. S2, S1, S0, and carry in 0, 0, 1, 0, 0, 0, 1, 0 for addition operation. Okay, and what else we need? Carry out goes to the overflow bit E. So to do it, look at over here. How we can go load the carry out to the overflow bit? By using a signal L. Look at over here. Load A. You see, you need to load the result in A plus carry out to the overflow bit E from ALU. So to perform this operation, you need the signal L. So L should be high at that time. At T3, L should be high. Look at over here. L is high at T3. All other signals are 0. All other control bits are 0. At T4, A plus B bar plus 1. That is A minus B. And carry out goes to the A. That means you perform subtraction operation, the result goes to the A register, and carry out goes to the overflow bit. So A minus B, right? So what is A minus B? Look at over here. It's the subtraction operation A minus B. And what is the control word for it? 0, 1, 0, 1. So look at over here. The control word is 0, 1, 0, 1. And we need to use make L equal to high to perform this operation, that is carry out goes to overflow bit and the result goes to the A raised L equal to 1. Clear? Now at cycle T5, it clear the overflow bit. How it clear the overflow bit? By using the signal W. Okay, by using the signal W. Okay, so signal W should be high. This is signal W, and signal W should be high over here to clear the overflow bit. T5, at T5, look at over here. It clear the overflow bit. Look at the flow chart. Look at the flow chart. At T5, it clear the overflow bit. Okay, so this is according to your flow chart. So how to clear the overflow bit? Make the signal W high. W will clear the E. Okay, at T6, what you do? You invert A. Okay, you invert it. That means not operation. Not operation. This is the not operation. Inverted. 1, 1, 1, 0. Okay, that means carry equal to 0 for logical operation. So triple 1, 0. So look at over here. Triple 1, 0. Cross means don't care, but we'll take 0 over here in a sense that because carrying has no meaning in logical operation. Carrying equal to 0 in logical operation. So we'll make it 0. And what is how to load A? What is the signal to load A? Look at over here. Okay, load A, L. L will load A. So L should be high. Okay. At clock cycle at function at clock cycle T7, what happens? Increment A. This is the increment of A and invert the sign of A. So how to increment A? Got over here. A plus 1. Increment A. What are the control word? 0, 0, 0, 1. So look at over here. This is 0, 0, 0, 1. And also you are going to load the result to the A register. So L should be high because you are going to load the result to the A register. And how you take the complement of sign of A? By using the, look at over here, complement AS, Z. Z will complement AS. So Z should be high. This is Z. Okay, Z should be high. So what we have done? We have written the control word or control output for different clock state T0 to T7. So now we have a table that will be the part of our microprogram. That means in our microprogram, at different clock state, this will be the control word output. Okay, that means for this operation, this is the controller. For this operation, this is the control word. At different clock state, different operation. So for this operation, this is the control word. Now we'll combine this operation to write our microprogram to perform 2's complement, addition, and subtraction. Okay, so let's write the microprogram now. Let's write the microprogram. Let's write the microprogram to perform 2's complement, addition, and subtraction. Okay, so what is the microprogram? Before writing the microprogram, we are going to write the pseudocode. That means algorithm, sometimes called pseudocode. Okay, pseudocode before writing the actual microprogram. So this is the symbolic microprogram. Okay, microprogram with symbols. For us, this is for us. This is the microprogram for symbol. Okay, look at over here. symbolic microprogram for control memory. Symbolic microprogram. For us, easier for understanding so that we can easily write the microprogram. So this is the symbolic microprogram. Look at over here at cycle T0. Cycle T0. If x equal to 1, initial state, it is at cycle T0 x equal to 1. And at cycle T0, if q is equal to 1, then we perform subtraction. Q is equal to 1. We perform subtraction and we go to T1. Yes, go to T1. And if QA equal to 1, QA equal to 1, then perform addition and go to T2. You see? QA equal to 1, then go to T2. And if QS and QA both are 0, that means no requirement for addition and subtraction, then don't go anywhere. Stay at state T0. First line. Okay? Now, at T1, what happens? At T1, this is the operation happens. At T1, what we do? We complement the sign of B. We complement the sign of B. At T2, what we do? At T2, if S equal to 1, we go to T4, and if S equal to 0, we go to T3. Right? So look at over here. If S equal to 1, then go to T4. Okay, then go to T4. And if S equal to 0, we don't need to write it, because if the condition is true, then we come to 4. From where? We come to 4. The condition is true. Right? But if the condition is false, if x equal to 0, we don't go to the 4. We come to 3. It's the next line. That means if condition is false, come to the next line. We perform, on the next line, we perform addition, and job is done. We go to T0. Now, when we come to T4, we take what we do at T4. At T4, what we do? Look at the here. A plus B bar plus 1. That's A minus B. We store the result in A, and we send the overflow bit, carry out bit to the E bit, E register. Okay, overflow bit. We send carry out to the overflow bit. So this is the operation at T4 we do. Okay, and also for it we have written the control word, right? Already know what will be the control word for it. At T5, after that what we do? We check the condition. At T5, we check the condition. If E equal to 1, then we come to, we make, go to 0. Setting 0 to E. By clearing E, we go to 0. If E equal to 1. Okay, so if E equal to 1, what we'll do? By clearing E, we'll go to 0. From where? We'll come over here. The condition is true. Okay, but if E is not 1, we will not go to 0. We'll come to, from where? We'll come to, if condition is not true, then we will come to over here. T6. This is the T6. Right? In T6, we will complement A. We will complement A at T6. Then we will come to T7. At T7, what we do? A plus 1, this goes to A, and we change the sign of A. After doing it, from T7, we go to T0. Clear? This is called symbolic microprogram. From the symbolic microprogram, we are going to write the actual microprogram. Now, this is the state T0, T1, T2, T3, T4, T5, T6, T7. 0 to 7, right? Now, this is the control word. This entire table we have just designed in our last slide. Entire table. This is the control word. that will perform the required operation at that timing state, at the T state, right? We have designed it over here. We have designed it. A different T state, a different T state to perform that operation. This is the control word for it. So we can directly just write this control word part over here. Okay. Now, every line of the microprogram is called micro instruction. Micro instruction, as you have seen in the last class, has three parts. One part is the control word. Okay. Let's say this is the line. For example, this is a single line. Enter. This is single line. This is single line. This is the control word for it. This is the control word. This portion is the control word. This portion. Okay. Now, every micro instruction not only has the control word, it has two more parts. One part is called the branch address. This is the branch address. That means, in case if you need to branch in some other location, okay, inside the program, this would be the address used to go over there. And whether the condition is true or false, that means if the condition is true, only then you load the branch address. Otherwise, you will not load the branch address. You will load the next line. So these are the branch control bit. Bit position 13 and 14, they are the branch control bit. This branch control bit will be tested with the bit in the flag register. If the condition is found true, then this branch address will get loaded in the microprogram counter and you will jump to that address. Like over here, look at over here. If the condition is true over here, s equal to 1, then go to 4. You will jump to 4. Okay? From T2, if the condition is true, you will go to T4. And if the condition is false, then you will not go to T4. You will go to the next line, T3. Same thing over here. So this is the branch address, branch control bit. This branch control bit will be tested against the bit in the flag register. Sign flag, zero flag, carry flag, and overflow flag. Okay, 4 flag. They will be tested against the bit in the flag register. If the condition is found true, then this address will be used okay, if the condition is true, then this address will be used to jump to that location. Otherwise, go to the next line. So look at the first line. If x equal to 1, at T0, x equal to 1. If QA equal to 1, then go to 1. How you know that QA will be 1? By checking this branch control bit with the flag register. So how to do it? Look at over here. This bit, pin number 13 and 14. What we have given in pin number 13 and 14, look at over here. We have written 0, 1. If you write 0, 1 over there, 0, 1. Load input to the control address list. Okay, load input to the control address list. How you load the input to the control address list? These are the input. If QA equal to 0, this is the input 0, 1, 0, 2. And if Q s equal to 1, that means if you want to perform subtraction operation, go to T1. This is the T1. 0, 0, 1 is the T1. Now 0, 1, 0 is the T2. So if subtraction operation, that means load input to control addresses. So if subtraction operation, this is the input 0, 0, 1. So this 0, 0, 1 will be loaded to the control address register so that you will go to address T1. 0, 0, 1 is T1. So you go to the address T1 if it is subtraction operation. And if it's the addition operation, then 010 will be loaded to the controller address register and you will go to T2. Okay, look at over here. So 01. For 01, load input to the controller address register. So this is for 001 for subtraction and 010 for addition. That means T1 will be loaded to the controller address register so that you come to T1 for subtraction operation. Go to T1. And for addition operation, you go to T2. You come to T2. Clear? So either you come to T1 or you come to T2. If you come to T2, then from T2 what you do? You see, from T2, if S equal to 1, then go to T4, and if S equal to 0, go to T3. Okay? So look at over here. When you come to T1 or T2, look at over here, T2, we have given 10. What is 10? 10. Load input to controller address register if S equal to 1. If S equal to 1, that means signs are different. Then load input to the controller address register. That means if signs are different, then this is the input address 100 T4. You see? From T2, this is T2. At T2, branch control bit is 10. So this 10, what it does? Load input to the controller address register if S equal to 1. If S equal to 1, signs are different, you need to go to the T4, not T3. So this is the address of T4. 100 is 4, T4. To perform subtraction operation. So if it is T4, at T4 you perform subtraction operation. And if S equal to 0, then you go to T3. If the condition is false, then you go to T3. At T3, what you do? You perform addition operation, and after performing the addition operation, you go to T0. You go to T0. Control branch control is 01, that means you load this address. After performing addition, you go to T0, job is done. Okay. Similar way, you fill up this branch address and branch control bit for this symbolic microprogram. Once you fill up, it looks like this. So the entire portion, this is the control one, branch address, branch control bit. These three parts make a single micro instruction. And how many micro instructions are there? 8 micro instructions. 1, 2, 3, 4, 5, 6, 7, 8 micro instructions. So this entire portion is called microprogram. This microprogram we are going to load in this hardware. Look at over here. Over here. This microprogram we are going to load in the control ROM, control memory. And everything other side of the control that you see, these are part of sequencer. Next is generator. Okay. This is the multiplexer that you check the branch control bit. You see, this is the 4 bit, 0 bit, sign bit, overflow bit. Okay, the 4 bit of the flag register that you test with. Okay, and this is the control address register, and this is the incrementer. That means if condition is false, you don't load the address, the control address register. You increment the control address register by 1 so that you go to the next line if the condition is false. And if the condition is true, then you load the branch address and you go to the location. So if I tell you this diagram, next address generator, control address register, control memory. Okay, so in this case, this is the control address register, control memory, and all other part is, all other things that you see is part of next address generator. So this is hardware part of your microprogram control unit, and in the control storage of ROM control memory, you store the microprogram. This is the microprogram that you store for them. This is the entire microprogram you store for them. Okay, so this entire design is called microprogram control unit. So what we have learned now, we have designed the microprogram control unit for two's complement, addition and subtraction. This microprogram control unit has three parts: control storage, control address register, and the sequencer. All other part that you see is part of sequencer. So what we have seen the steps to design the microprogram control unit. We have used a very simple problem, two's complement, addition and subtraction. So when you design the real hardware, your design becomes very complex. But how you solve the complex problem? You divide the complex problem into a smaller problem like this. Okay, and solve the smaller part. And as you solve each of the smaller part, you solve the bigger problem. That's why when you design a CPU, not a single people design the CPU. Sometimes hundreds of people get involved in the design of the CPU. Okay, a few dozens maybe people get involved in the design of the CPU because it is very big process. But in this theory class, we have given some effort to understand how the job gets done using a very simple problem: two's complement, addition and subtraction. So this is a microprogram control unit for two's complement, addition and subtraction, and we have gone through the process to write the microprogram. This is your microprogram that you store in the control storage. Now I'll give you a small problem. Another problem I'll give you. Okay, what is the problem I am going to give you? Based on the concept or understanding that we have gathered till now, you will solve it. What's the problem? Count the number of ones in a register R1. Let's say write a program, microprogram, to count the number of ones in register R1 and store the result in the register R2. This is the problem now. Count the number of ones in register R1 and store the counting result, how many ones in register R1 in a register R2. So R1 register will hold the word that you will count how many ones were there. After counting, that counting number will be stored in another register called R2. First job, we need to write the flowchart first. So this is the flowchart first. You are going to, this is the starting point. In our previous program, we stopped cycle T0 to T7. Okay, so we give cycle T8 over here. We start from T8, T9, T10, T11, T12, T13. Okay, so first thing, we initialize the register R2 0 because R2 will hold the count value, right? R2 register will hold the count value. So initialize the register R2 with 0. First thing. Then we initialize the carry bit with 0. We clear the carry bit. Now we check the register R1. If R1 is equal to 0, that means there is no one, right? If R1 register is 0, that means there is no one, so job is done. But if R1 is not 0, then certainly there is someone. So what we do? Circulate R1 with carry. Circulate R1 with carry. So when you circulate R1 with carry, let me draw something. Suppose this is your an 8 bit. Okay. For example, this is 4 bit, okay, and this is carry bit. This is carry. Initialize the carry bit with 0 bit. Okay, so when you take this bit over here, if it is 1, then 1 will come over here, and this 0 will come to this bit position. Okay, circulate R1 with carry. So each bit you take on the carry bit. Then 0, because the carry bit was 0 initially, it will come in that bit position, right? So if suppose this bit that you are transferring through the carry bit is 1, so if you check the carry bit, if carry bit is 0, then keep on circulating. If carry bit is equal to 1, then increment R2 by 1 to hold the count. Clear? So after incrementing R2 by 1, again we clear the carry bit. And we check R1 if it's 0 or not. If R1 is 0, then job is done. If R1 is not 0, then again circular R1 with the carry. Now again carry was 0, so 0 will come to so this 0 will go over here, and another 0 will come over here. Okay, this 0 will move over here, and another 0 will come over here. Okay, so again the bit you have taken on the carry bit, if it is 1, you increment R2 by 1, and again keep the same process. Get the carry bit, check register R1. If it is 0, job is done. If it is not 0, keep on circulating. So as you keep on circulating, after 4 testing, 4 steps of circulating, entire content of this register R1 will be 0. After 4 steps, right? It will be 0. So when it is 0, look at over. When R1 equal to 0, job is done. Job is done. But if it is not 0, that means we need to keep on circulating. In this case, 4 times we will do. So what happens at the end? This R1 will have 0 value, job will be done, and R2 register will hold the number 4. Clear? R2 register will hold the number of 1. So this is our flowchart for our problem. Count the number of 1 in register R1 and store the count result in register R2. So this is a flowchart. Step TA. So this is step T8, T8, T9, T10, T11, T12, T13. Again the same process. First write the control word, design draw the hardware part, take a hardware configuration, logic part and ALU part. ALU part, data processing part already have designed. You design the logic part. Okay, so you design the logic part, and based on the logic part, you write the control word. Based on the control word, you write the micro instruction. And combination of micro instruction is the microprogram. So you write the symbolic microprogram, then write the real microprogram. Okay, like this. This is the symbolic microprogram, then write the real microprogram like this. After writing this microprogram, design hardware like this. It will be different because different operation. So this ROM, this is the ROM and control address. These two components will be remain same. All other parts, this portion also will remain same. Like okay, you check the branch control bit with the flag bit, and all other parts will be different based on your algorithm. So we have shown you one example. The solution of counting the number of ones and instead of the result in R2, we have shown you the flowchart, but the rest of the design is your assignment or homework. You will not collect the homework. That means it is important for your exam purpose, but not for collection. You'll solve it by yourself as an assignment. Okay? And this is the end of your syllabus. That's the good truth. This is the end of your syllabus.